Okay, let's continue on the background section. So at the end of the lecture on Wednesday, we talk about the energy resources in the US. And we specifically mentioned the reliability challenges brought by integration of renewables. So because later we'll talk more in detail about the reliability criteria. So that is actually the one thing we have to satisfy through this entire course, because we focus on power system dynamic disturbances and how to model and simulate and control. So the conclusion from this slide is basically saying integration of renewable comes with some price. So renewable energies is not free. So you need to pay the price. If it's not for the fuel costs, you need to pay the price for building the transmission grid to make it strong enough to put the spending reserves to compensate the uncertainties of renewables. And also you may need new batteries, energy storage, or new controllers to provide additional grid support, because conventional generators such as single generator, they come with not just the generator itself, generating the energy from either kinetic energy of the water or the thermal energy to electricity. They also have the whole bunch of control system for frequency and voltage. So when you retire such power plant and you build solar farm, the solar farm need to provide similar control. Even it can be reduced level, not as much as conventional generator, but they need to provide some control. For this entire courses, we're not focusing on studying the problem for control of a solar farm or wind farm, but we'll learn some fundamentals and background knowledge. At maybe proper timings, I will just bring some real problems related to renewables so we can discuss how we can make the system better. Okay, let's continue. So this slide shows the AC power system structure starting from a generation until the end users. We can partition the system into 4 parts starting from generation. So by generation, usually we're talking about the generators in the power plant, which generate electricity from either thermal energy or from if it's hydro power plant, it will change from potential energy and kinetic energy of the water into electricity. So this part will stop at some transformer. So the power plant usually operated at not very high voltage, for instance, lower than 25 kV, because there's the higher voltage, the higher insulation challenge. So usually it's not operated at same voltage as transmission grid. So the electricity can be generated at 25 kV, then through a step-up transformer, so you can increase to transmission voltage level, so which is usually about 100 kV. So at the transmission voltage level, all the way above 100 kV, so you can increase voltage until maybe 765 kV. In some other countries, they have 800 kV or 1000 kV. So the higher the voltage, the lower current you need to carry to deliver the same amount of power, right? Because the power is the product of the voltage and current. If you increase voltage, you decrease current. By using the same size of conductor, you actually can deliver more energy. But the challenge will be definitely you need to have the large enough insulator. The 100 kV insulator definitely not work on 200 kV. So you have to upgrade the insulators. So in the US, the highest voltage level is 765 or 735 in some area. Most of the system is operated for the backbone network is under 500 kV. So if you go to the Cedar Bluff, you see very large tower. You should be able to guess what that level, the voltage is based on the length of insulator. If you like, you can take a picture, ask ChatGPT what voltage level is. It should give you a pretty good answer. So that's generation. For transmission, so after this step-up transformer, so you deliver electricity through the transmission line, the tower. So it's very, so the boundary between the transmission system and the next part, which is distribution system, pretty clear. For transmission system, you see towers everywhere. So those towers carry very high, very large conductors and long insulators. And along the transmission network, there could be some large industry load. Industry load, they can directly take a high voltage electricity and utilize for manufacturing. But for end user, we still need to have another part, which is the distribution system. But between the sub-transmission and distribution, there could be a system which is called sub-transmission. Sub-transmission is just connecting the distribution and the transmission. In most of the system model, sub-transmission is still considered part of the transmission, but operating at lower voltage. Typically, we can use 100 kV as a boundary, like between 100 kV and 138 kV. So if you see the voltage is from above 35 kV until 138 kV, so that usually belong part of the sub-transmission system. Distribution system is operated under 35 kV. So that is the voltage level you can go to feeders to power the buildings, homes, and farms of different users. Okay, so the focus of this course is covering generation, transmission, and sub-transmission. Okay, so we don't model in detail for distribution system. Later, if we have to build some model to finish the entire system, including both generation and load, the distribution system will be simplified by one concept, which is called bus. Bus means just whatever under a transmission substation or sub-transmission substation. We just integrate everything into just single equipment. We call it a bus. We ignore the details under the bus. In the section number 2, we'll talk about the load modeling. So you'll have a better idea how we can simplify the entire distribution system under a substation to become finally a bus. Then that bus will have a load. The load will be, if you still remember how we calculate power flows, right? We measure, so the power system has different type of buses. You have a generator bus. The generator bus will have, which is called PV bus. We have a specified power P and voltage magnitude. We need to solve angle and the rated power. And for load buses, we can give the P and Q, the active and rated power, but we need to solve voltage angle. So those PV buses actually what we call, each bus is actually representing one distribution system. It's just simplified distribution system. Any question here? Okay. All right, so I bring this table again. So for 421 students, you already you have seen this table before, but 522 student, it's very important to be aware of this table, because that can be very different from where the power system is operating in your regional country. Okay, the U.S. power system is very different. Okay, so if you attend any conference or talk to anybody working in the power industry, so there are always some like terms. It's okay, power company. So we work with power company, we work with this power company. So you can always ask a question, which type of power companies? Okay, there are so many different type of power company. Like I was from China, so in China, there are probably only two power grid. They have a state grid and a southern grid. Even those both grids are actually managed by government. And also in some European countries, they have maybe just a single power grid or single power company. There may be a very little providers at the end, but basically that's everything is managed within the same power company. But in the US, it's very different because that's what we call deregulation. So I will talk about deregulation in more details in the next slides. But what this table represents is telling when we say electric utility companies, what electric utility companies really mean. Okay, a brief explanation for electric utility company is some company, they own something in the power system. They have to own something. Yeah, you may think that's a pretty silly, dumb question, right? A power company doesn't own anything. How can they do business? They can. They definitely can do a lot of business. That's called deregulation. It's just like you sell computer. You don't have to manufacture a computer. You can just know this Apple store has price like a MacBook $1,500, and that guy is selling for $1,400. I buy someone from there and sell this store, right? So you can earn money. But electric utility companies, they have to own something in the power system. So this table show, yeah, that's already almost 30 years ago, but now the number should be much bigger than this one. Because at that time, this table doesn't count many renewable providers, right? It's still just conventional energy provider. So there was more than 3,000 electric utility companies in the US by 1996, right? Fewer than 1,000 companies were engaged in power generation. So which means only less than 1,000 companies own power generators. The others, they don't have generator. They have maybe transmission or distribution network. For those utility companies, there are a number of categories. The largest category is the first one is the investor-owned utilities. So those companies existing today, the main purpose is just to get more money. Right? So just do the business. So there are more than 240 such companies. Also, the new number is 360 such companies in 2015. But now it could be, I think this number won't change too much. Those are the companies, if you go to a website, you can find the stock price. They will influenced by the stock market. You can name some of the companies which are very important. Which means if you really want to become power system engineer, that's where you can find the job. They regularly hire engineers, right, and technicians. So EP is one large company, and American Transmission Company. Consolidated Edison is the power company operating in the New York City region. Dominion Power is the power company pretty much operating in the Virginia. Duke Energy is such as North Carolina. Energy is in Mississippi State or Louisiana State. First Energy is actually the area close to the north, near the border of to the Canada. And some company you can tell directly from the name, like Florida Power and Light, it has to be in Florida. But sometimes they may also operate neighboring state facilities. I will give some example later. So there's no way for Hawaiian Electric Company to operate not in Hawaii, right? So it's a pretty largest company in Oahu Island. There may be some others, but basically Hawaii Electric is the power company there. National Grid is a power company from UK, not America, but they operate some of the power system here. Okay. What else? Yeah, I mean, Pacific Gas Electric, that's the largest power company in North California. A lot of graduates from this department actually joined that company. In South California, so this is the Southern California Edison. That's operate in Los Angeles, San Diego, near the but close to the border. There's another power company called San Diego Electric and Light. Okay, so there's so many companies even in California in one state. Okay, so those are the pretty large power companies. They take 66% of electricity generation. The second type is publicly owned utilities, right? So they have a long history starting from some authority managed by the government, but now they still have some aspect from the governmental operation, but they are individual power company. So their purpose is not to make money for investors. They just try to serve the local area. Some examples such as like a New York Power Authority is the power company in New York surrounding New York City. The inside of New York City is a consolidated Edison. The surrounding New York City is a NYPA, a New York Power Authority. Long Island Power Authority, that's a power company in Long Island. Okay, it's also near the New York City area, but it's in Long Island. So okay, let me finish this one. So those are the, usually the name come with some power authority. Okay, that's, and the third category is very interesting, right? You see the Tennessee Valley Authority, even it's called the Tennessee TVA, but it's not the Tennessee local power company. It's a federal government-owned utility company. So that's very interesting, right? So if you work for TVA, you work for federal government, not for Tennessee state government. Another example is this BPA. That's actually the power company in Northwest on the West Coast. That's also operated by federal government. Another one is called the WIPA, the Western Area Power Administration. So when I work at EPRI as project manager, I deal with most of power companies. So by quick look, I work with directly, right, with the engineer for more than probably 20 of the company in this table. For some company, I didn't mention, I didn't work directly with them, but we have contact and meeting. So for project managers, if you work, try to help those power companies, it's very important to know which type of company they belong to, because they have, you encounter different type of paperwork. So with local power company, that's easy. Investor-owned power company, pretty easy. Deal with state government, the federal government, that's totally different thing. Okay. If you remember in the 421, we mentioned the Norris Dam, right? There's a hydropower plant. That's one federal government project. That's also almost about the beginning of the TVA. So federal government spend money on some really large project on hydro and nuclear. That could be some of the reason why the TVA is still operated by the federal government. That's not very common in the US. The third one is like just very local, smaller power company, but the number is pretty large. The last one is very interesting because the first time I showed this table back to 2013, and there's a category called independent power providers. Independent power provider, which means you just own a power plant due to some reason. Who knows? You just have this power plant. You want to sell electricity, then you connect to a local, depending on where you are. You find a local utility to see whether they can connect your power plant or generator for solar farm or wind farm to their grid. If that's done, you become independent power provider. You sell electricity through their grid to the users. At that time, the wind farms are not specifically mentioned in this category, but later, a lot of renewable energy operators actually can fall into this category. Yes. So another example, if you remember, for 421, we mentioned wind farm. We mentioned Buffalo Mountain Wind Farm, right? That's part of the TVA. That has at that time about 13 small wind turbine, probably 5 or 6 large wind turbine. If you drive to Oak Ridge, you will see the wind turbine on the mountain. So that can be considered, that farm can be considered like independent power provider, but they connected to the TVA using TVA system to deliver electricity. Okay, so far all the companies they owe something. All right. Oh yeah. So one example I want to mention is I'm doing a project with using under a NASA funding. That one is to study how to operate chargers, not for electric cars, but for electric flight or aircraft. They're interested to find two areas, right, to study. So one area they want to investigate in Tennessee. I mean, the people who found the funding is not from power system. They're from transportation, from other area. They want to do the study. One is in Tennessee, the other is in New York City. I told them that's not two good locations to select because Tennessee, TVA is federal-owned power company managing only transmission system, but under TVA, there's many smaller power companies. So there's no such like a Tennessee power company existing in the world, right? You deal with many utility companies. And New York City is even more complicated. New York City, if your charger is placed, cover the New York City area, you need to deal with Consolidated Edison. If that's in the Manhattan area, you need to deal with Napa, that's surrounding the Manhattan area, and you also need to deal with LIPA. And also National Grid also operate part of that system. And there's even 2 or 3 more local power company there, right? There's no such a New York City power company in the world, okay? So that's the reality. But that's good for students. You can find, if you want to become power system engineer in New York City, you have many places to go. Yeah, question.
Study of electric flight. Like I know you said that you're studying it, but how long has that people looked into that, like electric flight?
I think technology is pretty okay right now, but they basically public acceptance of such technique, right? So eVTOL is pretty mature. eVTOL, which is called electric vertical eVTOL vertical. Yeah, I don't remember the full name, but anyways, that's like basically like a drone, but it's operated by people, not helicopter, but they can fly it or at lower elevation. Sure. Yeah, but that's a NASA project. It's not like a really industry project. So you just look into future how the electric grid is ready to accommodate a lot of charging load in the system. Okay. Yeah. Yeah, that's why they want to pick New York City, because New York City have a lot of people who want to pay for that. Yeah, we don't pay for that, right? In Tennessee, we can drive. Yeah. Yeah, you can drive electric car. Okay, next we can talk about deregulation. Deregulation is about the competitive U.S. power market. So what does deregulation really mean? So I have some generators generating electric power at some location, and I have some users who want to use the electricity. In a fully regulated power system, there's one company who own the generator and then connect to the transmission. So basically own everything in the previous slides, right? The structure one, everything, all the 4 parts of system. But in the deregulated, the power system structure, any participant can only participate. You can decide only participate part of this entire path, not from a end to end. You can only participate in generation or participate in distribution. So the government will set down some rules and laws for the market participant, such as electric utility companies, independent power providers. ISO I will explain what they mean. And also there's some trading company. The trading companies just play with the strategies, bidding strategy to help their members or customers to earn money. So it's profit oriented. So let's assume we have some generation owner. Some companies own the nuclear power plant, some own the hydro power plant, some of the solar farm. And there could be another company who owns the transmission. Okay, so the generator need to be connected to the transmission system owned by some different company. Then the transmission owner may not own distribution system. So which means the owner only have the voltage up down to 138 kV, but under 138 kV, that's somebody else system. So they need to connect to a distribution system owner network. And distribution owner may sell electricity directly to end user if they want, but there could be also another level, a service provider. They can just build a program, build maybe plans, different plans for user to choose from. Okay, so any company can decide to participate only on one part of this entire path. But if you want, you can participate from the beginning end to end. That's still the case in some areas. Deregulation means you don't have to do everything. But if you participate in any element in this picture, you need to follow all the rules and laws. But if you decide to do everything, that's also fine. So later we'll show in pretty large area in the US, they're not free market. There's some type of market, but not like a fully deregulated market. Then there will be a question. So if everybody just participate in part of this picture, so who is managing this picture? Definitely we don't want government to do it, right? So we need another company. And the condition that company shouldn't owe anything. If the company owe transmission, that could be a problem. They will try to maximize their profit. So we need some company who don't own anything in this picture, but they operate everything, almost everything. So such companies are called independent system operator. So they operate the system, but they don't own anything. So that come back to my the beginning terminology. We mentioned power companies. In general, power companies may mean utility companies or ISOs or anything here. So you can call some independent system operator as power company, that's fine, but they are not utility company. So if you call them utility company, they have to own some of the facility in the system. The ISO determine the electricity price by bid-based security constraint economic dispatch. Okay, so you're supposed to understand what this sentence means, except for the bid-based, but you should be able to know what security constraint economic dispatch mean, right? The last session in 421 was all focusing on how to address this problem, formulate and solve this problem. But here we just add a bid here. So the ISO will determine a nodal price at each location in a day-ahead market. They try to match offers from generation owners to bids from consumers at each node. They calculate a supply-demand equilibrium of the power flow on hourly basis. They determine the price at least on hourly basis. A locational marginal price, or LMP, is defined as the weighted average for the nodal price for one area. So for each area, they can generate such a LMP, which is basically just weighted nodal prices for that area. So in the real-time market, the LMP is actually calculated to balance the differences between day-ahead and commitment and actual demand. So that's how the market is operating. Professor Fran Li has maybe power system economics class, so that one will cover in more details on how the market is operating. So if you have interest, you can take in the future. Okay, so this map shows all the ISOs we have not in the US, just in US, in North America. So there are, when we see independent system operators, there are seven ISOs in the US and 2 ISOs in Canada. So totally there's 9 such organizational companies. So basically they don't own infrastructure or facility or anything of the system, but they operate the power system in that area. This figure is pretty old, but if you find like today's ISO or RTO, there's some other map, but this is still the most accurate one. So by today, by 2025, there's still only such ISOs. There's some other companies between utility company and ISO, some other organization to help on the market. They can show up in like in the northwest area, such as what one company is called Western Power Pool. But that's still not ISO by definition. Okay. But I also put like a regional transmission organization, RTO, together with ISO. ISO is at the beginning, that's a regional concept to operate the power market, because California ISO, that's mainly operated in California state as independent system operator. You remember the California have many utility companies. They have a Pacific Gas and Electric. They have a Southern California Edison. They have a San Diego Electric Light. They also have many smaller companies. So they need one operator to operate the entire California market. So that's the first one, implementing the full deregulation in California. So for the other company following California ISO, they still call them like ISO, but later there's some FERC, which is Federal Energy Reliability Commission. They define new responsibility like ISO need to take. So they create another terminology, RTO, but you don't have to differentiate. Even I don't know the difference is very tiny. Most of people, whenever you see, okay, I work with ISO, or I work with RTO or ISO, or I work with RTO, they are all treated the same. Okay, basically they are doing almost exactly the same thing. Okay, let's see. So we are in Tennessee, right? We don't have any ISO because we have at the transmission level have a TVA. TVA basically is not fully deregulated. It's still somehow regulated power system, operated by TVA. And in the large area of southeast, there's no fully deregulated power market, and all the color area they show almost fully deregulated power market. Another interesting story is you see this map is updated 2015. Before 2015, this part of areas belong to Southwest Power Pool. Okay, the Southwest Power Pool is bigger. And the Mid-Continent ISO only take this part. At that time, the Mid-Continent ISO is not called Mid-Continent ISO, it's called Midwest ISO. Then they take this part to join MISO, to quit from SPB and join Midwest ISO. Then Midwest ISO changed the name and logo, everything to MISO, Mid-Continent ISO. And what is interesting is for this pretty large area, this is power company called Energy. It doesn't have physical connection with the rest of MISO. So they operate by the same system, but they have two different regions, not physically connected. Yeah, that's how the market is working. It doesn't have to be in the exactly same power grid. Any question? All right, so yeah, let's talk about from economic dispatch to electricity market. In traditional economic dispatch, so if I'm the power company knowing all the power plant, I want to minimize my fuel costs based on the knowledge of the load, right? So I'm going to solve this optimization problem. So I have my cost function. The PI is actually the generator output of each power plant. So C is actually the fuel cost. I want to minimize my total fuel cost. And I want to maintain the power balance to make sure the total generation is equal to the total load. Sometimes you also need to add another term just to compensate the transmission loss. But then you need to solve power flow to know the accurate loss. And this is some constraints, inequality constraints, saying that each power plant need to only operate power within this range. Go beyond either limit will cause some reliability problem. The economic dispatch problem is trying to find out the equal incremental cost, right? Does this one sound familiar to everybody? Okay, it's just after winter break. Okay, so right. So you remember this example. Just show one example. So if each cost function, how the fuel cost change with the power output is, for instance, like a second order function of quadratic function, then we can calculate how the cost increase with the power. We call it incremental cost. So which is first order derivative of cost with respect to each generation. So that should be a linear function, roughly linear function. So in this plot, X is the power output, Y is actually the incremental cost, the physical meaning just the electricity price. So the different power plant will change the price in different straight line, will increase the power output. So what the economic dispatch problem is trying to address is to draw a horizontal line. So that horizontal line will move up and down. If you gave, let's say, my target is to power totally 800 megawatt demand. So you will move this horizontal line up and down until the 3 intersection point gave you the power output, like 150, 250, and 400. The total exactly match the 800 megawatt. Okay, so you solve the problem. That's it. That's a price. That's the electricity price. Everything is transparent within this market. No market, but in this dispatch. That's economic dispatch. However, in the electricity market, as I said, the people doing such optimization belong to working at ISO, right? The fuel cost is not fully transparent information to ISO. What power company can provide will be some bidding strategy. They will still provide the curve, but that curve doesn't really mean the actual fuel cost. So why should you do that? Because that under some condition you can maximize your profit. So supplier may bid strategically to maximize their profit. One example could be, for this case, if I treat generator 1, this generator as one power company, the other generator as another second power company, then all together by second power company. And the second power company know this first company has output limit only at 450, okay? So if I run both my power plant, they total only just generate like 400 megawatt power. Is there any way I can make my power plant generate more and at much higher price? So we can, right? So I can just retire one of the 2 units. If I retire this unit, not retire, I just outage this unit. I can say, okay, this unit is about the timing for this unit to do maintenance. Let's just disconnect this power plant. I only let the other power plant operate. And my other power plant, if the limit doesn't have to be 250, I can make it bigger. So what happened is, so this is 400, this is 450, but in order to generate 800 megawatt power, this power plant will generate 350, right? Totally to make up 800 at very high price. You can do the math. You can try all the combinations, right? To play with all different strategies to disconnect this unit or that unit or both. You can always choose the strategy which give you the largest benefit. So you can play with the market. So that actually happened in the first few years when the deregulation was implemented in California. So there's terminology called California electricity crisis. That basically means what happened shortly after the full deregulation in California around 1999. Okay, so what happened is before the passage of the deregulation law, there was only one stage 3 rolling blackout. Stage 3 rolling blackout means if the power company decide the reliability will be compromised, they can intentionally shut some load or disconnect some generator for the reliability of the entire system. This is basically you cannot reduce the load, which are important, like hospital, airport, but you can just trip some unimportant load. Before this law is passed, there's only just one such blackout in the history. But quickly after the passage of the law, the California has 38 such blackouts. So most of them are caused by the poorly designed market system that was manipulated by the traders or the market participant. They just try to maximize their price, their profit. So in order to sell electricity at much higher price, some traders intentionally encourage suppliers, which are power plant or the power companies, to shut down some plants, right? So for the remaining power plant, they can sell electricity at much higher price. How much higher? You can read from this figure. So this figure has two type of curves. One is like roughly like monotonically increasing, which is supply curve. So there are three supply curve. The solid line is actually what happened at let's see, 16 o'clock. So the broken one is actually what happened at 12 o'clock. So you see the supply. There's some change in the supply curves. Each supply curve tell. So that's basically similar to the fuel cost. So if I generate more electricity, the price will be higher. The fuel cost will be higher. So that's increasing with the power. Another type is demand curve. Demand curve means so if you sell electricity at lower price, as a user, I can decide to use more. So that go opposite. That's usually they're declining. Many users are very flexible. At a higher price, I will use less, but a lower price, I use more. So that's why the curve will be declining. So it intersects with the supply curve. That will be the market equilibrium. For example, we consider like a 12 o'clock. The 12 o'clock, this will be the equilibrium. So that determines the price at 12 o'clock, which is $50 per megawatt hour. So that's what happened at 12 o'clock. But if the supply curve doesn't change, because if the supply curve is only based on the fuel cost, there's not strong reason for the fuel cost suddenly increase, right? So if you remain on the same curve, will be the new price after 4 hours at 4 o'clock, 16 o'clock, 4 p.m. Okay, so the price only just double. No, that's okay, because like 4 o'clock, that's close to the peak hours. But the supplier gave a different, because the demand increased. So they, instead of gave the old curve, they changed their supply curve. They moved the supply curve to the left to intentionally to intersect with the demand curve at much higher point. So this is the new equilibrium. That's about $160. That's almost 3 to 4 times bigger than the price at 12 o'clock. Okay, so if the suppliers and traders they play with the market, that will cause a lot of interruptions or disturbance on the system. How do we prevent this one? Then there's so we need some reliability standards. So NERC, North American Electric Reliability Corporation, this is a company to create standards. So at the beginning, it's just a non-government organization formed by electric utility industry back to 1968. 1968 is 3 years after the first large power blackout in the U.S. It tried to promote reliability of a bulk power system in North America. Initially, the membership is voluntary, which means a utility company, you can decide whether or not you join this organization. Why do you want to join organization? You can work together with other power company to make new criteria, new standard, everybody can follow. So we can always operate the system at the same page. You can also decide not to join, but later this one become mandatory. Starting from 2007, FERC, the Federal Energy Regulatory Commission, actually granted NERC the legal authority to enforce reliability criteria. Everybody, as long as you are utility companies or ISO, you participated in the market or electricity operation, you need to follow the standards made by NERC. So now become mandatory. They need to comply with the reliability standards. Following any power blackout or large power outage, and there will be some investigation which can take half a year or longer to investigate what was really happening. If there's a violation of the standard, they need to pay the penalty, and the penalty will be utilized to train your engineers to comply better with the standard. All right, so we'll continue on next Monday. So because the snow, we don't know what's going to happen in the weekend. So just in case the campus is shut down, we'll have the lecture by Zoom. But I will send a notice either in the evening of the Sunday or the early morning on the Monday. Okay, pay attention to the announcement on the campus.
Is it definite that the lecture's going to be on Zoom?
I don't know. I'm not aware. Yeah, I don't know. Yeah, if Monday is drivable, I'll be here. We'll still have the lecture.
Thank you.